Hi, this question is about the motion of satellites. So there are four satellites A, B, C, and D, and the satellite B and A have the same mass as well as D because they all have the mass small m. In their orbits, they are moving around the two planets. Both planets have the different masses, so it masses m and its mass is 2m. So and you know one thing, that mass of the satellite is not important. If the two satellites C and B are moving in the same orbit, then they will have a same orbital speed despite of the difference of their masses. So I mean to say they will have a same speed VC as well as VB, right? Because in this question we have to compare the time periods of the satellites, okay? So why they have a same speed? Because if you know this equation, the orbital speed is the instantaneous speed of the satellite, and it just depends on the mass of planet divided by the distance from the planet. So in this case, this distance is 2r. Since the both have the same speed as well as this one as well, gm over 2r. So don't you think that they will cover their orbital motion in the same time, which means that the TB is equals to TC. Okay, so we have filtered in a very less time the two options. So the right option should be one of them. Okay, but I will explain you in detail, right? Because in these two diagrams, we see that not only the speeds are different. For example, the speed of VD is not equal to the speed of VA. Okay, so rather the distances and masses are also different. So we should we should choose such a equation that directly links the time period of the satellite with the orbital distance of the satellite, right? Which means that the time period, and we have one equation, the square of time period is proportional to the orbital distance of the satellite, right? And it is the famous, what do we call it, Kepler's third law. So this is the Kepler's third law. Now, if we relate it, okay, let's complete it. So t square is equals to, if we place a constant, so it is equals to 4 pi square over gm generally, right? But in our this question, this small m is not constant because the two planets have different masses. So if we just rearrange it, right, and t square is equals to, we can write it like this, 4 pi square over g, and here we have the r cube over m, right? Now this thing is a constant, right? So which means that the t square is directly proportional to r cube over m, right? So if we apply this proportionality, you can investigate, and in fact, why not, if you take a square root, so you can write it like this. So t is equals to the square root of 4 pi square over g can be written as constant k and r cube over m, right? So we notice that the time period is directly proportional to the square root of r cube, orbital distance, and time period is inversely proportional to mass, right? S- So let's start from the satellite A, right? The satellite A have a mass m. So we can say the time period of the satellite A is equals to the square root of, k is a constant, which is same constant for all of them. Its orbital distance is r cube, r, which is the distance from the center of the planet, okay, and divided by the mass of the planet is m. So this is the time period A, right? Now the time period for the B will be equals to, so TB is equals to, the constant is k, and look at the distance. It is at a distance 2r. So it will be 2r whole cube over, it is orbiting around a planet which have a mass m. So it is 2 cube, right? Which is 8 basically. So k r cube over m, you can take this square root of 8 outside, which can also be written as 2 square root of 2. And inside we have kr cube over m, right? So which is, by the way, it means that the TB is equals to the 2 square root of 2 times ta, which is obviously the satellite B will take more time as comparable to the A, because A is orbiting very close, so it will have a very high speed. All right, that's why it is taking less time. I think it should take least time among all of them, right? So now let's talk about the C. So for the satellite C, which is also orbiting around the same planet, right? And its mass is m, but its mass is not important. You have seen in equation. So don't you think, according to this equation, we will write the same thing, and eventually you will get the same result, and which means that it is also equals to the 2 square root of 2 times the time period of A. That means that the time period of the satellite B is equals to the time period of satellite C, okay, which we already concluded from the other equation of the orbital speed, from the orbital speed. Let's talk about that satellite D, right? And it is orbiting around this planet, which have a twice the mass as comparable to this planet. So let's see, does it make any difference or not? So TD is equals to the square root of, so K into its orbital distance is 2r divided by 2m, right? So that should be equals to, now inside the square root, you can write it like it is 8 r cube divided by 2, so it would be 4 k r cube over m, right? Which can be written as TD is equals to uh 2 square root of k r cube over m, which means that the TD, the time period of the satellite D, is equals to the 2 times of time period of satellite A. So now it helps us to rank them, right? So the TA must be least, then the time period by the satellite D, and the B and C are the slowest satellites because they are taking maximum time to complete their one rotational motion. So I hope you understand this question.